This video will cover section 3.7, applications of integrals to business. In this video, we'll cover consumer and producer surplus as well as continuous income stream. Let's begin by discussing consumer and producer surplus. Here are demand and supply curve for a product. The demand curve is decreasing since lower prices are associated with higher quantities demanded and higher prices are associated with lower quantities demanded. Demand curves are often shown as if they were linear, but there's no reason they have to be. The supply curve is increasing. Lower prices are associated with lower supply and higher prices are associated with higher quantities supplied. The point where the demand and supply curve cross is called the equilibrium point, and it's given as a quantity and the price depends on the quantity. So in this image, we would have the blue curve as our demand curve because it's decreasing. The red curve would be our supply, and this point of intersection would be the equilibrium point, where demand and supply are equal. Suppose that the price is set at the equilibrium price so that the quantity demanded equals the quantity supplied. Graphically, the amount of extra money that ended up in consumers' pockets is the area between the demand curve and the horizontal line. So we're looking at this blue triangle in this graph. This is the difference in price summed up over all the consumers who spent less than they expected, a definite integral. Notice that since the area under the horizontal line is a rectangle, we can simplify the area integral. So what we're looking at is the integral from 0 to the equilibrium price or quantity of the demand curve minus the fixed price. That's the top minus bottom to get the area in between. And if we distribute the integral over the subtraction, we end up with the integral from 0 to the equilibrium quantity of the demand curve, and then the integral from 0 to the equilibrium quantity of just the equilibrium price. This is just a constant, and that ends up just being the equilibrium price times the equilibrium quantity, and this is the consumer surplus. For the producer surplus, the amount of extra money that ended up in producers' pockets is the area between the supply curve and the horizontal line at P. So this is going to be your producer surplus here, below the equilibrium quantity and price and above the supply curve. This is the difference in price summed up over all producers who received more than they expected to. Similar to consumer surplus, this integral can be simplified, and so we end up with something similar where we have the equilibrium price times the equilibrium quantity minus the integral from 0 to the equilibrium quantity of the demand curve. And again, that's because we started with this difference between two curves where we do top minus bottom, which is the P minus the supply curve. So formally, given a demand function where price is given as a function of the quantity and supply function where P is also given as a function of the quantity, and we can find the equilibrium point where demand equals supply, then the consumer surplus is the integral from 0 to the equilibrium quantity of the demand curve minus price times quantity. And then similarly, the producer quantity would be price times quantity minus the integral from 0 to the equilibrium quantity of the supply curve. The sum of the consumer surplus and producer surplus is the total gains from trade. The units are price per item times the number of items or quantity of items, which ends up in just being the money earned. So the demand and supply functions for a certain product are given by P equals 150 minus 0.5 Q and P equals 0.002 times Q squared plus 1.5, where P is in dollars and Q is the number of items. Part A asks to decide which is the demand function. In this case, our demand function is going to be P equals 150 minus 0.5 Q, and you might assume it's because it's the linear function, but really the reason we would choose this function is because it is a decreasing function because it has a negative slope. So you can look at it and identify that it's linear in terms of Q, where price is a function of Q, but it is decreasing because the slope is negative. And you can always graph this in your calculator to verify that. So our demand function as a function of quantity is going to be 150 minus 0.5 Q. This is our demand. That tells us that the supply function is then our quadratic function. So S of Q will be 0.002 times q squared plus 1.5. And this is supply as a function of quantity. We want to find the equilibrium price and quantity. And remember, equilibrium occurs when demand equals supply. So for part B, we'll set our demand function equal to our supply function and solve for the quantity. We'll plug that back in to find the equilibrium price. This is a quadratic equation, so I'll work to set this equal to 0 and then use the quadratic formula to solve. So when we use the quadratic formula to solve, we end up with two values, negative 424.79 and 174.79. You can find these by using your graphing calculator. Obviously, we want to work in decimals because our original functions are given in decimals, but money is also written in decimals, not fractions. And so we can't have a negative quantity, so we're not going to consider this negative number through the rest of our work. We'll only be considering the 174.79, and those are our number of items at our equilibrium point. I'll plug this back into either the demand function or the supply function to get the corresponding price. I'm going to plug it back into demand personally because it's linear and so it'll require less work. So we end up with P equals 150 minus 0.5 times the Q that we just found. And so the equilibrium price, I'll identify this as Q star and P star to stay consistent with our notation on the previous slide, is going to be 62.61. Again, you can plug that into your calculator to find those values. In part C, we're asked to find the total gains from trade at the equilibrium price. And remember, total gains are consumer surplus and in the sum of producer surplus. So we'll calculate consumer surplus and producer surplus separately, and then we'll add those together to get our total gains. Starting with consumer surplus, we have the integral from 0 to the equilibrium quantity of the demand function minus the equilibrium price times the equilibrium quantity. So we're looking at the integral from 0 to 174.79 of 150 minus 0.5 q dq minus 174.79 times 62.61. This is where I'll now switch to go over how to use the graphing calculator to integrate.
84 for this demonstration, but please feel free to use any graphing utility you find on the internet. Start by pressing Map and choosing Function Integration by choosing number 9. On my calculator, an integral will appear. For the lower limit, we'll start with 0, and for the upper limit, we'll put 174.79. Where the integrand will be our demand function, which is 150 minus 0.5q. We'll need to use x since q is not an option in the calculator. We want to make sure to also integrate with respect to x. We'll subtract off the equilibrium quantity times the equilibrium price, which is 174.79 times 62.61. The total of which is 7,637.01 if you round to the nearest decimal.
Next, we'll find our producer surplus by setting up the integral, which is the equilibrium price times the equilibrium quantity minus the integral from 0 to the equilibrium quantity over the supply function integrated with respect to Q. So we have 174.79 times 62.61 minus the integral from 0 to 174.79 of 0.002 q squared plus 1.5 because that's our supply curve. We'll go back to the calculator to calculate this value as well. By entering the equilibrium quantity times the equilibrium price, which will be 174.79 times 62.61. Then we'll subtract the integral. You'll press Math and choose Function Integration, which is number 9. The lower limit will still be 0. The upper limit is the equilibrium quantity, which is 174.79. The integrand this time will be the supply function, which is 0.002. We'll use x again, x squared plus 1.5, and we'll make sure to put dx. Consumer surplus is 7,121.35 when rounded to the nearest decimal place. And so our total gains are the sum of the producer surplus and consumer surplus. And again, taking it to the calculator, we end up with a total gains of $14,758.36. Let's talk about continuous income stream. Recall from earlier chapters that compound interest, if we have P as the principal or the initial investment, R is the annual interest rate expressed as a decimal, then A of T is the amount in the account at the end of T years. If we're compounding N times per year, it would be P times the quantity 1 plus R over N to the NT, where N is the number of times it's compounded within a year. Alternatively, if we're compounding continuously, it's P times E to the RT. If you're using this formula to find what an account will be worth in the future, T is greater than 0 and A of T is called the future value. If you're using the formula to find what you need to deposit today to have a certain value P sometime in the future, T is less than 0 and A of T is called the present value. You may also have learned somewhat more complicated annuity formulas to deal with slightly more complicated situations where you make equal deposits equally spaced in time. Calculus allows us to handle situations where deposits are flowing continuously into an account that earns interest. As long as we can model the flow of income with a function, we can use a definite integral to calculate the present and future value of a continuous income stream. The idea is each little bit of income in the future needs to be multiplied by the exponential function to bring it back to the present, and then we'll add them all up, which is a definite integral. Suppose money can earn interest at an annual interest rate of R compounded continuously. If we let f of t be a continuous income function in dollars per year that applies between the year 0 and year t, then the present value of that income stream is given by the integral from 0 to t, f of t times e to the negative rt dt. The future value can be computed by the ordinary compound interest if it's being calculated continuously. You'll use pe to the rt, not b. So let's look at an example. We want to find the present and future values of a continuous income stream of $5,000 per year for 12 years if money can earn 1.3% annual interest compounded continuously. So we're having 5,000 deposited every year, and every year it can grow continuously at 1.3% for those 12 years. So we do have a function. It just happens to be that the function is 5,000 and it's a constant. And so the present value would be the integral from 0 to 12, the number of years, our function, which in this case is 5,000, times e to the negative 0.013, that's our rate, times t dt. And then we'll go back to our calculator to calculate this. And 16 cents if you're rounding to the nearest decimal. Alternatively, if we're finding the future value, in this case, our principal would be 5,000 deposited. It's still earning 0.013%. And so the future value would be 5,000 times e to the 0.013 times 12 because it's for 12 years. And using your calculator, you'll see that's $5,844.13. That concludes the discussion for Chapter 3.